Welcome to the final of the Department of Education seminars for this term. I'm absolutely delighted to be introducing Jenni Ingram to speak today. This is a seminar that's been convened by the Pedagogy, Learning and Knowledge group, and I think it encompasses all those elements of the theme. Diane Mayer is usually the theme convener, but since Diane is in Australia, this is not a good time to be introducing anybody. So I'm really delighted that the opportunity to introduce Jenni has fallen to me, because Jenni's work in mathematics education. So Jenni's an associate professor of mathematics education here in the department, and obviously the work that she's presenting on today, the TALIS video study, it's hugely relevant to kind of keen focus of Jenni's work about, you know, classroom interactions, what's going on in the classroom. And you know, this is the UK element, that study, the UK observation expert. I think that's Jenni's title within the TALIS video study. It's you know, really sort of significant large scale work, but Jenni's research is sort of the commitment behind Jenni's research is about sharing the insights of that with teachers. So Jenni, I find, a kind of extraordinary colleague to work with for this kind of breadth of vision of what's going on in mathematics education nationally and internationally, that's, you know, represented by her work, you know, on the TALIS study that we're going to hear about today, combined with an absolute commitment. And, you know, the other parts of her work are about working with trainee teachers within our initial teacher education programme. But her vision about how do we take that research and share it with and learn from, you know, local mathematics teachers who are, you know, seeking to learn from research and understand how to make use of it in their practice, but also raise up new questions for research as a result of their practice. So it's an enormous pleasure to welcome Jenni today. Just to outline, Jenni's going to speak for about 45 minutes, and we hope that will leave you know, plenty of time for questions at the end. So we should have at least 15 minutes for questions at the end. So without too much further ado, and having given 4 minutes, I think, for people to get into the room, so I hope that's allowed all those to join us. It's a real pleasure to hand over to Professor Jenni Ingram. Thank you.
Thank you. So I'm just going to share my screen. Okay, so I'm just going to talk about the TALIS video study results from England. So the United Kingdom was just one of 8 countries that took part, and within the United Kingdom it was just the schools within England that took part. But this was a 4-year study that was just published a couple of weeks ago. And you'll see from the names on the front slide, these are all the people that were involved in the England part of the study. So you've got the team at Oxford, which is myself, Ariel, Pam, Peter, Tianak, Christine, Kyla and Miranda, as well with our partners, Elaine, Anna and Naomi from the Education Development Trust. And we also worked closely with an international consortium, which was the OECD Secretariat and RAND, ETS and DIPT, who were all involved in the design of the study. So it was a massive collaborative effort between all of these parties. So the aims of the study were to look at 3 different aspects of mathematics teaching. So we wanted to understand how teaching practices, specific ways of teaching, were related to student learning and student non-cognitive outcomes. We also wanted to observe and document how teachers from the different countries or economies taught. And we wanted to explore the interrelationships between these teaching practices and the relationships among contextual aspects. So we also collected data about teacher characteristics, teachers' educational experiences, student characteristics, and classroom teaching and learning, so what went on in the classroom. So it involved 8 countries. In the planning stage, there was a 9th country. The USA was taking part at the very early stages of the project. So in this early stage, all of these countries were involved in the design. And then the 8 countries actually took part and collected videos. So these countries, it wasn't the entire country. So in England, it was only England from the UK. It was just Shanghai from China. Then you had Madrid from Spain. There were 3 regions in Chile, 3 regions in Japan, and we had Germany. And then additionally, we had Mexico and Colombia took part as well. And I'm just going to report on England tonight, but you'll find all the details of all the other countries on the OECD website for the TALIS video study. So in terms of the sampling, the project used a stratified 2-stage probability design where 100 schools were randomly selected using exactly the same list as the TALIS 2018 study. And at the same time, we chose 200 replacement schools. Once a school had been randomly selected and consented to taking part, then within that school, a mathematics teacher was randomly selected, and they just chose which class they were going to be teaching for the study. We only accepted classes where at least 15 students or 50% of the students consented to taking part. So if a class was too small, they weren't able to take part. Each country or economy aimed to recruit 85 teachers, which is exactly what England managed to recruit. But there are quite a lot of sampling deviations across all of the countries, meaning that for half the countries, including England, the sample of teachers is not necessarily representative of all maths teachers. So if we have a quick look at the England sample, our 85 teachers came from 78 schools. The average class size was 27.4 students. All the schools that took part were state funded, but in the random selection process, there were some independent schools, but none of them consented to taking part. And 3/4 of those schools were in cities. 58% of the teachers were female, which is in line with what happened in TALIS, but the average number of years teaching experience was 10 years, which is quite considerably lower than in the TALIS study. And then we also asked them some questions about their professional development and their education experience. So around 1/4 of the teachers who took part had a master's level degree, and 69% had taken mathematics courses equivalent to those needed for a degree at some point. That could have been in their first degree, or it could have been as part of their teacher education. So within that sample, we also had 2,024 students, and they were mostly in year 10, so about 71% came from year 10, but we also had some classes that were in year 11 and year 9 and year 8, but most of them are in year 10. They chose the class that was being taught the topic of interest. So TALIS video study just focused on one topic. So this topic was chosen because all of the countries that were taking part all taught this topic to a similar age range of students. So it's quadratic equations, in particular, the solving of quadratic equations that this study focused on. And you can see from this slide that roughly all the countries participating taught this topic to international grade 8, international grade 9, which equivalent to England would be year 10 and year 9. You can see that the average age that students are taught this topic is between 14 and 15 years old. But what you can see that's a bit different is the number of lessons that quadratic equations is taught for. And you'll see that England is towards the lower end of the range there. But also in England, we teach quadratic equations at the same time as quadratic functions. But you'll notice that this is not true in all countries. And in particular, Japan and Shanghai, quadratic functions is an entirely different subject. So it's not taught at the same time as quadratic equations. So the focus of TALIS video study was specifically on the teaching of quadratic equations. So when we looked at what we meant by quadratic equations, we were specifically looking at the different methods that you might solve a quadratic equation that are in the curriculum. So we had solving by factorizing, solving by using a quadratic formula, or solving by completing the square, or finding the roots of a quadratic function through a graphical method. So this is called opportunity to learn within the study. This is a widely used term in international comparative work, and it refers to the idea that the amount of time that you spend learning something is related to what you learn. So it's how much exposure do you have to the content that you're trying to learn and how that affects your attainment within that topic. So how often were you exposed to solving quadratic equations by factorizing, and how does that relate to how well you do on tests measuring your ability to solve quadratic equations by factorizing? We didn't just look at solution methods. We also looked at ways of working with quadratic equations. So these are split into 4 topic areas. We've got opportunity to learn algebra, which is about manipulating quadratic expressions, such as expanding or factorizing brackets, using the binomial formula, which maths teachers will be familiar with, but in England we tend not to call it the binomial formula until A level, but we still use it when we're teaching how to expand brackets. There's also reasoning, where we look at the different cases depending on whether the coefficients A, B and C are present or what their values might be. So considering A being 1 as one case, but A being greater than 1 as a separate case. And then we can also connect it to functions by using graphs and making connections between the graphs. And we can also apply it to a range of different contexts. And those contexts could be real world context, or they could be contexts within mathematics, but in other areas. So all these subtopics were measured in all of the countries that took part. So the TALIS video study was aimed to be a longitudinal design, but the length of the study was over the topic of quadratic equations. So before the topic was taught, all the teachers and the students have completed a questionnaire which collected data about their characteristics, but also their attitudes towards the learning of maths, their experiences of learning maths in the past and at the present. And the students also took a specifically designed pre-test. So for this study, the test focused on number work, numeracy skills, and a little bit of algebra, anything that would be considered a prerequisite for quadratic equations. They were then taught the topic of quadratic equations, and at the end of that process, they completed another questionnaire. So there's a second teacher questionnaire, a second student questionnaire, and then there was a post-test which focused on quadratic equations. So in these questionnaires, the students and the teachers were asked to reflect back over the lessons they had during the topic. So we have their perspectives on what was going on during the lessons. But we also videoed some lessons. So in the study, we recorded 2 lessons, one towards the beginning of the unit and one towards the end of the unit. And we also collected any lesson artifacts that accompanied those lessons and for the lesson that followed. So we had a total of 2 videos, but 4 sets of artifacts. Now, the artifacts include worksheets, they include the PowerPoint presentations that they were used, they could have included pages from a textbook or any resources that were being used, but they did not include students' work because the focus of this study was on the teaching rather than the students. Okay. We did collect lesson plans, but they weren't very common, so not much emphasis is being placed on those. But when we came to analyse them, we treated the artifacts as a set. So all the coding was applied to a set. So that was the PowerPoint and the worksheet and any resources that we used in the lesson, homework, for example. Okay, so the lessons and the artifacts were coded. They were specifically coded according to a framework that was specifically designed for this study. And that's where all the countries came together. We met several times to design the coding framework, drawing on existing research, but also thinking about aspects of maths teaching that the countries highly valued, but weren't necessarily the focus of many of the other projects that are around. And I'm going to focus towards the beginning of this talk on those topics, rather than the features that are frequently looked at, such as classroom management or the social and emotional environment of the classroom. Okay. The camera, because we're interested in teaching, the camera was always focused on the teacher, but it did capture quite a large proportion of the students. Then for the main study, there were 3 outcome measures that we were interested in. So the first one was a measure of student learning, and this was measured through students' attainment on the specifically designed pre-test and post-test. But we also had some questions in the student questionnaires relating to their self-efficacy, that is, their confidence in their own ability to do the mathematics. These questions largely came from the PISA questionnaires. So there's a lot of similarity and overlap, with a couple of additional questions from other research. We also collected data on students' own interest in mathematics, how interesting they felt in mathematics, and that again was on the pre and the post questionnaires. So for self-efficacy and personal interest in maths, the data was collected on 3 aspects: their self-efficacy or interest in maths with their previous maths teacher, their self-efficacy and personal interest in maths with their current teacher, and their self-efficacy or personal interest during the topic that was being taught. So these were the 3 outcomes, student outcomes, that were of most interest to the study. But we were also interested in the teaching that was going on. And the teaching was looked at across 6 different domains, and I've color-coded these. So the first 2 domains are classroom management and socio-emotional support, which are about the classroom environment. Then we had discourse was another domain, and then assessment of responses to student understanding. These were much more about the quality of teaching and the instruction, but these were generic aspects of teaching, so they could apply to subjects other than mathematics. And then we have 2 at the bottom there, which is the quality of subject matter and engagement in cognitively demanding subject matter, where the items within those codes were very specific to mathematics. So what does it mean to cognitively engage in mathematics? Within each of these domains, we had 3 different types of measures. So from the videos, we had 2 measures. We had video components, which were higher inference, and these were rated every 16 minutes within a video. And then we had video indicators, which were far lower inference, and they might just record whether something was present or not. For example, whether there was an interactive whiteboard or not, or whether a student used a calculator or not. And these were rated every 8 minutes. And then we also had measures for the artifacts. These only applied to the teaching domains, so that's discourse, assessment, quality of subject matter, and engagement in cognitively demanding subject matter. But these would rate the artifacts like the lesson plan, the PowerPoint, the worksheet. And all of these ratings were completed by specifically trained raters with different raters for each measure. And every video and every artifact was independently rated by 2 trained raters. So I'm going to go through the key findings. These are the headline findings of the study before I focus a bit more on the mathematics teaching that we saw. So as you probably would expect, students with a higher pre-test score tended to have higher attainment on the post-test score. And the pre-test scores explained about half the variation in the post-test scores. But interestingly, students who had more opportunity to learn quadratic functions, that means that they had more lessons where there was some aspect of quadratic functions included, tended to have higher post-test scores. And particularly relevant to England, the class also had an impact. So students in lower attaining classes, where the average attainment of the class was lower, had lower post-test scores, even after accounting for that individual pre-test score. So their own attainment explains some of the outcome on the post-test, but actually the class attainment also had an effect over and beyond that. So which class students were in made a difference in terms of attainment. There was also an interaction effect, which is shown by the graph, where the average class attainment makes more of a difference to students with higher prior attainment. So in the study, we grouped classes into 4 groups depending on their average scores on the pre-test, which is similar to the way that students are grouped in schools. So they're often put into 4 different sets for mathematics. And you can see from the lines of the graph that if you have average attainment on the pre-test score, which was 200, you can see that depending on which class you're on, with that score of 200, would have a different effect on your post-test score, with those who had a higher class average receiving a higher mark than those that were in a class that were in the lowest quartile. In terms of self-efficacy, in general, well, on average, students who had higher self-efficacy in mathematics with their previous teacher also had higher self-efficacy with their current teacher, with pre-self-efficacy scores explaining about 1/5 of the variation in their current self-efficacy scores. However, we also found that their opportunities to learn reasoning, so their exposure to reasoning types activities, so those are the activities where you consider different cases depending on the coefficients of a quadratic equation, they had higher general self-efficacy in mathematics. In terms of personal interest, students who had a higher personal interest in maths also had a higher personal interest in maths with their current teacher, with their previous personal interest explaining about 1/8 of the variation in students' current interest. So students who experienced more opportunities to learn algebraic operations, so that's factorizing, expanding, working with equations and functions, and reasoning about the different types of quadratic equations, tended to have a higher interest in the mathematics. In terms of what we saw through the videos, there were no significant relationships between the different teaching practices on those 6 domains and the student outcomes, which were post-test marks, their self-efficacy with their current teacher, and their personal interest with their current teacher, if you did not take into account student or class characteristics. But when we did account for the class characteristics, such as student prior attainment or class prior attainment, we did tend to find some differences. For example, after accounting for student and class characteristics, the class average pre-test attainment made more of a difference to post-test scores for students in classes with teachers who had lower ratings for classroom management. So the classroom management ratings on overall were very high. So you can see the scale there goes from 3 to 4. The scale overall was a scale of 1 to 4, with 4 being the maximum possible. And almost all the teachers were in that top range of 3 to 4. But you can see if you were towards the bottom end of that, so an average rating of about 3.3 for classroom management, which class you're in made a difference to your post-attainment score. Whereas if you were right at the top there in a very well managed class, it didn't really matter which group that you were in. For post self-efficacy scores, after accounting for student and class characteristics, teachers who had higher average ratings for either classroom management or for maths instruction, the maths specific domains, which were the quality of subject matter and student cognitive engagement, that made a difference to students' post self-efficacy scores if the students were in classes who had the lowest average pre-self-efficacy score. So if one's ability to succeed in mathematics was in the lowest quartile and you had a teacher who had a higher average rating for classroom management than most teachers within the study, or a higher average rating for mathematics specific instruction, then your self-efficacy score after being taught the topic was significantly higher. In terms of personal interest or your interest in mathematics, after accounting for student and class characteristics, students in classes with the highest teacher ratings for discourse and assessment combined, the class average interest in maths with the previous teacher made less of a difference to individual personal interest in mathematics with the current teacher, except for those that were in the classes that had the lowest average personal interest in maths scores. Now to the bit that I find most interesting, which is the teaching that's going on in the classrooms. So just to describe a little bit more about what we saw in classrooms. So again, one of the aims of the study was to observe and document how teachers from participating countries or economies teach. So having a look inside the classroom. And I'm going to take these in reverse order. So I'm going to start with the bottom row because this is math specific, and it's one of the key contributions this study is going to make to our understanding of the relationship between teaching and learning. So I'll introduce you to, first of all, to the quality of subject matter domain. So if you remember that we had 3 separate measures on each domain. We had the video component measures. These were higher inference. They were rated every 16 minutes, and they were always rated on a scale of 1 to 4, where 4 was the highest frequency of something happening or the highest quality. At the other end, we had artifact components, which were always measured on a scale of 1 to 3, and we looked at the whole set of materials in one go. And then in the middle, we've got video indicators. Some of these were just whether things were present. These were rated every 8 minutes. So you'll see that there's types of representation there. That was just, was there a picture? Was there an equation? Were there numbers? So that was just present or not. But others, such as real world connections or the explicitness of learning goals, these were measured on a scale. And those scales could be from 1 to 3 or 1 to 4, occasionally 1 to 2, but the higher number always represented the higher rating. So let's focusing now specifically on explicit connections. So you can see here's some examples from the videos from England. And you can see in the left-hand picture, you've got a teacher making connection between the equation, the quadratic equation in factorized form, and the roots on a graph. And on the right-hand side, you've got 2 pictures from the same lesson where the teacher is making a connection between the minimum point of a quadratic function and the completed square form of an equation. The most common connections in England were between graphs and equations. But we could also see examples where they made connections with diagrams. And then there were also connections made with other mathematical topics. There were also connections made with real world connections, but these were very rare. They were measured in 2 ways, and yet we found very few examples of connections to the real world. We did find examples where they connected to prior learning, so connecting quadratic equations to linear equations, for example. And we also found some connections to future learning, so connecting to complex numbers and looking at non-real roots. There were also opportunities for teachers to make connections between different methods. So there are 4 common solution methods for quadratic equations taught in England. And you could, for example, derive the quadratic formula by completing the square and make a connection between those 2 methods. But within explicit connections, we can also connect to the second component, which was explicit patterns and generalizations. So these were also seen particularly in lessons where teachers were using dynamic geometry. So here the teacher was varying the coefficients of A, B and C using the sliders that you can see on the left-hand slide. And then the students were noticing how that affected the shape of the curve. So you're looking at a pattern across several different representations of a curve over time. So you can see there's a connection here between the algebra and the equation and the function, and at the same time the students are working with patterns in how a particular change in a coefficient affects the shape of the function. But there are also other examples of explicit patterns and generalizations. So we saw them in some of the tasks that students were used. Now, explicit patterns and generalizations is one of the examples of a component that was chosen specifically because all the countries thought this was an extremely valuable part of learning mathematics, that patterns and generalizing from patterns underpins a lot of mathematics. So this is very difficult to measure. It's very specific to the maths classroom. We took as our definition of a pattern, we defined it to be an ordered set of mathematical objects, which could be numbers or equations or graphs or even problems, or it could have been a recurring sequence of some type. And then a generalization was a deliberate extending of the range of reasoning or communication beyond the case or cases being considered. Okay, looking for commonalities across cases. And there needed to be at least 2 examples before we consider something to be a pattern. There had to be a generalization across more than 2 examples. So if we now look at the scores. So clarity was not included in the final study. You can probably see from the images there that clarity is rather skewed towards the higher end. Almost all the lessons were very clear. The students showed that they were following the lessons, which was how that was rated. So clarity didn't correlate well with the other measures. So when we talk about the quality of subject matter in all the reports, what we're talking about is the explicit connections and the explicit patterns and generalizations. Now, a score of 1 on either of those means there was no connection, or there was no pattern, or there was no generalization. So England, although these look quite low, they were low across all the countries. And England had the highest average rating for explicit connections across all the participating countries and economies. And their second highest average rating for explicit patterns and generalizations after Shanghai. So although these figures are rather skewed to the left, they were higher than the other countries, most of the other countries taking part. From the indicators and the artifacts, we also found that 68% of the lessons had some form of explicit learning goal. And 54% of teachers had at least 1 artifact set, so this could be the PowerPoint or it could be a worksheet, with a learning goal that focused specifically on student learning. So the alternative there was just the topic. So if it said solving quadratic equations by factorizing, that counted as an explicit learning goal, but not one that focused on student learning because it was a topic. Real world connections were very rare, and 26% of the teachers who took part included no real world connections in any of their lesson videos or their artifacts. Connections to other mathematical topics were also rare, not including quadratic functions. And then 69% of teachers regularly connected mathematical representations. We saw a lot of equations being connected to graphs. The other math-specific aspect was student cognitive engagement. So the video components that are of interest are engagement in cognitively demanding subject matter, multiple approaches or perspectives on reasoning, and understanding of the mathematics that was going on. So engagement in cognitively demanding subject matter, we were looking for evidence of questions that ask students or tasks that ask students to analyze, synthesize, create, evaluate. Multiple approaches could be comparing and contrasting different methods, or even just the ability to choose which method to use to answer a question. And then for understanding a subject matter, we were looking at whether students were either asking why questions or whether they were giving explanations that focused on why something might be the case. And then in indicators, we asked about metacognition. So were students self-reflecting on their learning? We looked at their opportunities to practice, and we also looked at the use of technology. And those are replicated in the artifact components. So if we look at student cognitive engagement, again, you'll see that there's a skew towards the left of the graphs. So the average rating for engagement in cognitively demanding subject matters was a rating of 1.96. On average, looking at the domain overall, where we have an average of 1.86, this average was relatively high amongst all the other countries, second only to Japan. So although these figures are low, actually that was found across all the countries that were taking part. So all the teachers asked students to engage in analyses, creation or evaluation work at some point, at least once. So all the teachers were doing these types of activities. But some teachers never gave their students an opportunity to use more than one approach or to compare approaches. So there were some students who never had the opportunity to use multiple approaches. Students were rarely asked to engage in metacognition, but this was recorded through the indicators, so that may not have been the most appropriate way or easiest way to measure that. There are other ways that we might ask students to engage in metacognition that would not have been captured in the study. One thing that does stand out, all of the teachers gave their students plenty of opportunities to practice. So practice was measured in two ways. The indicators measured what proportion of the time was spent practicing, and then the artifacts had looked at the number of questions students were given to practice on. And England had the highest average rating for these. So for the artifacts, we had an average of 2.96 on a scale of 1 to 3, where 1 was there was no opportunity to engage in practice, and 3 was the opportunity to do it for at least half of the time. And we were the highest out of all the countries on the opportunities to practice. Technology was a key focus of the study, but what we actually found is that teachers weren't really using technology. Pretty much every lesson had an interactive whiteboard and a projector, but they were generally used just to communicate. It was just to talk through a PowerPoint. There was not very much evidence of software being used to support understanding or anything interactive beyond communication. Only 10% of the lessons involved software at some point that would be considered to support learning. We also had some questions on the questionnaire about how difficult students found the lessons. So there was a range of questions. I've just given you 2 examples there that aim to measure how cognitively demanding the lessons were. And as you can see from the students who are in green, and they felt that the lessons were more cognitively demanding than their teachers, which is the blue graph. Now, if we look at teaching practices as an outcome, classes with a higher average score on the pre-test experience lessons with higher average ratings for student cognitive engagement compared to classes with lower average scores. So lower attaining groups experience less cognitively demanding material than higher attaining classes. Now I'm going to go quite quickly through the next lot of slides because they're not math specific, but just to give you an overview of the study as a whole. So the next 2 components were discourse and assessment. Just for people who will be paying more attention to this, we looked at the nature of discourse, we looked at questioning, we looked at explanations, we looked at the opportunities students had to discuss things in lessons, and we also, with the artifacts, we were looking for PowerPoints or worksheets that asked students to give an explanation, and that could have been of how or why something was the case. In assessment, it was about how much student thinking was there in the lesson, and then teacher feedback in the lesson, but also the alignment of instructions. How often did a teacher react to something a student had done, and how did that affect the lesson that followed? Teacher feedback does not have the normal meaning that it has in England pedagogy discussion. For it to count in TALIS Video Study, there had to be a conversation. So it couldn't be a student saying something and the teacher giving feedback. The student would have to come back and the teacher come back again in order for that to count as feedback. It had to be a conversation. We also looked at persistence, so that was whether students were supported when they were finding things difficult, whether students were required or asked to share their work publicly, and whether they were encouraged to evaluate their own learning at any point. So results were very similar to all of the countries that took part. The nature of discourse is the extent to which the discourse was teacher directed and focused on the level of detail when students contributed. Questioning focused on the nature of questions, and explanations focused on, were they focused on the deeper aspects of the mathematics or quite superficial aspects of mathematics? But these findings were very similar across all of the countries that took part. 17% of teachers had some form of discussion opportunities in their lesson that were focused on the learning objectives. So the discussion had to be about the mathematics that was being considered for it to count. But the artifacts rarely asked students for explanations. So there were plenty of explanations by the teachers. There were not so many explanations from the students. There were also some questions about teachers and students' perceptions. So most of the students and the teachers felt that there were opportunities for them to discuss their mathematics and for them to explain their ideas. But you can see also that teachers were more positive than students were about whether those opportunities were there. Significantly, classes with higher average socioeconomic status, that was measured through the number and the type of home possessions, as well as parental education. They had higher overall discourse ratings than classes that had a lower average socioeconomic status. And classes with higher average scores on the pretest had a significantly positive association with the higher overall discourse ratings than classes with a lower average on the pretest. If we move on to assessment now, again, these were very similar across all the countries. I'll just give you a second to read that. But you've got eliciting student thinking was a mean of 2.83. Teacher feedback was quite low across all countries, but that might be due to the way that it was measured. Aligning instruction had a mean of 3.25, giving an overall mean for the domain as of 2.7. We also asked teachers and students some questions about the way that teachers adjusted the teaching in lessons. So the teachers and students both reported that lessons were adapted to meet the class's needs, but it wasn't always done through giving different work to different students. So significantly, classes with a higher proportion of female students, or a higher average pre-test score, or a higher average level of parental education, or a lower proportion of students who spoke English at home, had higher average ratings on the assessment and responses to student understanding domain. These averages were taken, each teacher had, so they were averaged across raters, across segments, across lessons, so that you had one average rating per teacher. So moving on to the last two, which were classroom management and socio-emotional support, these two are measured in most international comparative studies that are based on videos, and so they exist in quite a lot of observation schedules already. So we looked at routines, monitoring how much the teacher was aware of what was going on in the classroom and the number of disruptions. We looked at what proportion of the lesson was time spent on task. Were students working individually, or were they working in pairs or small groups, which is what we called activity structure. And we also looked at how long lessons were. Within social emotional support, we looked at the respect, whether people were showing respect to each other, encouragement and warmth, and then whether students were willing to take risks in their learning. And actually in England, classes were really well managed. There were lots of evidence of routines and monitoring, and very few disruptions. And this was similar across all the countries. But 95% of the lesson segments included whole group work. So whole class work is similar proportion to most countries and only slightly less than Shanghai, where it was 99.6% of the lessons. But England had a higher proportion of segments of individual work than any other country. So we spent more time with students working individually. So we had 84%, Japan had 77%, and Shanghai had 68%, and all the other countries were lower than that. Pair work was similar across all of the countries, but England was lowest for the amount of group work, with Shanghai being the second lowest at 4%. So this was measured every 8 minutes. Teachers and students also both perceived the lessons to be well managed. But again, the teachers were more positive about the disruptions and the behaviour in classrooms than their students. These questions are the same questions that appear on the TALIS 2018 questionnaires. So you'll see these are slightly more positive than the results from the TALIS survey as a whole. Social emotional support, again, we did very well. We've got quite high scores there. teachers and classrooms were generally socially and emotionally supportive. And again, we asked the students and teachers some questions about this, and both teachers and students felt that classrooms were emotionally supportive, but again, the teachers were more positive than their students. So we asked them both about their feelings in the classroom, but also as an individual. So did they feel like their teacher cared for them, and so forth. So these were very positive, and they were positive across the board. There was only one significant finding within both of these domains, and that was that teachers who had taken some form of maths course equivalent to a degree at some point were found to be more supportive than those who had not. Okay, I'm probably yeah, I'll just do one more slide and then we might have to end because I think we're out of time, Catherine. So opportunities to learn. Just so that you know, on average, we spent 7.6 hours on the topics. But in England, these 4 solution strategies are not in the curriculum for every student. So in the foundation tier for exams, they only are required to solve quadratic equations by factorising or by finding roots of a quadratic function. Using the quadratic formula and using the completing the square were only in the higher tier syllabus at the point where this data was collected. So the opportunities to learn were collected in 3 different ways. We asked the teachers how many lessons they'd spent on the topic overall and what they'd taught in each lesson. We also recorded it through the lesson artifacts, so we looked at what the lesson material showed, and then we also asked students in the post questionnaire whether they'd seen questions like this. So we collected this sort of data in 3 different ways. I'm going to skip that. Significant findings. There was a greater extent of opportunity to learn was experienced by students with higher post-test scores. That's not perhaps surprising if we've got 2 tiers. So some of the classes would have been foundation tier classes, so would not have had access to some of the opportunities to learn. But they were also experienced with students who had higher post general self-efficacy scores and with higher post personal interest scores in mathematics. And then just for the teachers that are in the audience, there is now a Global Teaching Insights website that is coordinated by the OECD, and the videos from this study where there was consent to share them have been made available, and they've been connected to each of the domains here. So England did not take part in this bit, so there are no videos from England, but Shanghai and Japan, Colombia, I believe, they did take part. So there's 4 countries in there in total, and you can get a glimpse of what some of the maths teaching that was captured looks like. So I invite you to go and have a look at this website, and there's quite a lot of opportunities to develop your own practice. There's quite a few resources on there to support you thinking about your practice. Okay, and then there's the standard disclaimer that I have to show. And I'll hand back to Catherine.
Thank you very much, Jenny. And there's obviously, you know, such a huge wealth of data within the project, and a huge task to present, you know, as much of it as you did. And I'm glad you were able to play to your interests and focus on the mathematics. But thank you for sharing the you know, additional insights more broadly into aspects of teaching.